Hello there, welcome to another problem session. So today we have a problem from this website. You can go check more problems there at that website. This problem is a hard problem, I would say, for introductory physics level. So what are we supposed to do? This is the area which is a cylinder, infinitely long cylinder. You can imagine this whole thing is coming out at you, and magnetic field is just coming right at you. So this magnetic field means magnetic field is coming right at you, and this is just a cross section. So if this is like a z-axis, then this thing is xy plane, for instance. And there is a bar here. This is conducting bar, this thing, and so we're supposed to find out what's the EMF that will be induced in the bar between this point and that point. So what's the definition of the EMF? EMF, if you have a DC situation, then it's a voltage across the source. That's the EMF of a battery, for instance. You have a EMF in electrostatics, you can say potential difference. But here you don't have electrostatics. Here you have electrodynamics, so you have to be very careful. And the EMF definition, EMF between say 1 and 2, P1 to P2, this EMF is actually minus integrate P1 to P2 electric field dot dl. So dl is going from here to there. So this is an integral. So we basically, you can say I have, say this is O, and so this is the x-axis, and this whole thing is along the x-axis. So if this is a dx, so the dl will be like a dx I hat. And at that point, there's some electric field we need to figure out at that point. So E dot dl will be the x component of electric field. So at that point, dx, so this will be an integral. So this integral will be minus that. So minus. So this point will be some x1, and this point is some x2. So x1 to x2 dx, which is a function of x maybe as you go along, dx. So we have to do this integral, and so we need to figure out what the electric field looks like. At all these points. So that is the EMF. A related, so that's what you have to show. I just want to tell you another related point where it turns out if you do an integral over another path, say this path. So if you do E dot dl over this path, so if say this is C2, this is path C1, so path C1. So you do minus, so you go point P1 to P2, E dot dl, but we go through path C2. So you get an EMF something prime, it's a new EMF between P1 and P2. And then you'll find that this is not equal to what you got earlier. This is not equal to P1 to P2. E dot dl C1. Now if you say statics, in the statics this will be equal, but in dynamics this will not be equal in general. Okay, in this case it will not be equal. I would suggest after I'm done with this problem, maybe you want to do this problem, but I will just do this problem here. The problem is just going from here to there on this path. Okay, now this is a hard problem, and if you know how to do it, parts of it, maybe you want to go ahead and do it. I'll just pause. Okay, let's do this out. So what do we have? How do we proceed? Well, we need to figure out electric field, and the only thing here is we can try to figure out a circulation electric field. So Faraday says if I take a loop, and this is oriented loop, and in that loop we do minus E dot dl. So this is the entire loop. This is just a part of this. It's not entire loop question, right? So this is EMF in this loop. So this is the loop, and that will be equal to d dt b dot n hat dA. So I usually do this minus, I put minus on the other side. That's a normal thing to put minus on the other side. And what is this? This is over the surface, this surface. That's the surface, and this is the this part is going around this loop. So let's first figure this out and see if we can use that knowledge to figure out electric field. Okay, so let's how do we figure this out? In here, let's try some arbitrary point. We're trying to figure out some arbitrary point P. So that point P, so that's the point P, and we imagine that we have a circle that goes through that point P, and so this is going to be my circulation, this. And when we have a right hand rule, normal is going to be coming out. So normal will be coming out of that using for that area, for this integral. So circulation at maybe this radius is r, so let's call it CR at radius r. So this will depend on the radius, and so this is the surface up to radius r. And if you look at it, this is the only thing that has a time dependence. So this whole thing is going to be b dot n is just coming out. So that's going to be equal to b as a function of t. And this is uniform. It's the same everywhere in space, according to this. Then this comes out of the integral. And so we just get d dt b of t times the area is pi r square, and r is up to that point, so this r is not changing in time. So this whole thing is just, this is the time derivative, and everything is like that. So we get a circulation E dot dl, circulation up to this r, is just this. Now, this actually looks very similar to Ampere's law, which is in Ampere's law you do have circulation of magnetic field instead of electric field, and then you have a mu naught I enclosed. So this whole thing is like on the right side here, and this only depends on r. So we don't expect this to depend on, maybe direction depends on something, but in this case, if this depend on r, so this is kind of like if you had a problem where you had a magnetic density depend on r, current density depends on r, then if you had like a thick wire and you want to know the magnetic field at that point, so you'll do this circulation. So the B here was some B at distance r, and E had phi direction. This is the phi direction going around. So this is like a B of phi component. E had phi. So this is here. So by analogy, we just say, you know what, electric field in this problem will this is a claim I'm going to make, and just by analogy, I'm not justifying this is exactly the case, because a magnetic field obeys another law that makes this useful proposition. But you're going to do this way. Here there are no other charges, anything involved, so a very similar argument can be made here, and we say there will be phi component, and so this I'm going to claim like this. So if I go out here, what's the dl at any, so the dl, if you look at the dl by a small component, dl will simply be this r d phi E hat phi. So if I put it in there, I get 2 pi r from integrating on phi, and E component of phi component of electric field. This is thinking in terms of 3-dimension and spherical coordinate, because this is spherical coordinate. So this will be equal to minus dB dt by r square. So E phi at distance r is, if you can look at that, equals to minus dB dt r over 2. So we found the electric field, and now we just have to do that integral. But we need to have x component of this. So this is phi component. So electric field dot I hat will be the EX component. So EX will be that. And so this is, I've got a minus dB dt r over 2, and E hat phi as minus sine phi I hat plus something j hat dot I hat. I don't need to know that, because I hat with I hat will be the only thing surviving. This will give me 0, and this minus becomes plus dB dt r sine phi over 2, and r sine phi is this is phi, so this is just y direction, and that's in here. It's given at a distance, this distance, and this is d, and this is r. So this distance is r sine phi is simply equal to this y. So let's call that y. This is just simply y, and y is fixed for all the points here. So y over 2 dB dt. Okay, let me erase some of this and then try to do this out. Okay, let's get a more bold stuff. So this is we had a minus go from x1. So this is x1, and this is x2. Go from go from x1 to x2 ex dx, and ex is this x1 x2 y over 2 db dt dx. Now this is independent of x. Okay, so that's just equal to minus y over 2 db dt x2 minus x1, that's x2 minus x1, and that's equal to 2d, and 2 cancels out, and so and if you remember y in this 90 degrees here, and this is r and this is d, so the y is just y is square root of r square minus d square, so minus d is square root of r square minus d square db dt. Okay, so so it doesn't say the sign part here, and the question is about EMF absolute value, and that's just dB dt absolute value, d is square root of r square minus d square. Okay, so that's the answer for this problem. So I was also saying that maybe some extents of this problem are a little more interesting actually. Okay, so here is a extension of this problem, extension that I will strongly urge you to do this out. So you, instead of this bar, you had this bar, and but it was exactly same point between same 2 points. These are written just for clarity. So what will be EMF P1 prime to P2 prime? Well, you find out. Let's do this out, okay, together. So what we need to do integral over this C2, this path from here to there. So P1 prime to P2 prime, and we need to do it E dot dl and take a minus sign. That's the answer. And the E induced was E phi, E hat phi. Okay, and what is E phi? E phi was let's see, when it's decreasing, so it's going to be minus dB dt, and minus dB dt, this y over 2. This was like r over 2, not y over 2, and E hat phi. So that's what it is. But over here, dl was I hat dx. But over here, dl now is, so this r at every point is capital R. So this one is actually capital R and on this path on C2. So dl is going to be r d phi E hat phi. So when I take a dot product, I get a this gives me 1, and then I just multiply that, and none of them depends on phi, So this is a phi is defined according to x-axis. So this is say phi 2, and then from here to here is phi 1, and this angle is pi minus phi 1 and pi minus phi 1, and this angle is the same as this angle based on those symmetry. So that's equals to phi 2. So this whole thing is when you do the integration, I get, let's look at absolute values. So in the absolute values, I'm gonna, well, not necessarily drop the absolute value, just keep the sign dB dt r square over 2, r times r square over 2, and then phi gives me phi 2 minus phi 1, and phi 2 minus phi 1 is phi 2 equals to pi, phi 1 equals to pi minus phi 2. So this is equal to dB dt r square over 2 pi minus 2 phi 2, and 2 phi 2 is simply, phi 2 is simply, if this part is d, so this part is d and this part is r, and this is phi 2, then this is phi 2 is basically phi cosine phi 2 is d over r. So I can just do r cosine, so this is equals to dB over dt times r square over 2 pi minus 2 times r cosine d over r. Okay, so I did that one. Maybe you want to do some other shapes. Say you put a bar which is like goes from here all the way there. So this is another third bar. So what's the EMF across this bar? EMF across this bar. Now you can do that. That's another extension. So you find out that unlike in the statics, so if you have a statics, so in statics, let me write that down. In statics, not this dynamics, if I go between here and here, I'm going to have a unique value. I go this way, this way, this way, all going to be exactly the same values. That's connected with conservation of energy, you might remember. But here, in a dynamic situation, that's not the case, okay? So actually, if you were to have a, how about I go all the way and come back, I'm almost over there, okay? So I just look at this circuit. I come back, so it's really not zero. There is an induced EMF in that circuit. Versus if I go this way, say I go this way, I make another circuit which I take a big wire and go this way. I'm going to have a different voltage in this circuit than I'm going to have the voltage in this other circuit. So that's another problem that you can actually do. Let me extend it again for you to practice. Okay, same type of B situation. So we have this and the B is coming out. Same. So I take a wire, so make that loop, and so find the EMF in that loop. In this loop, Now take a wire and same place and make this loop. So I started from here and came back to the same place, but I went to different paths. What's the EMF in this loop? And you will find out that they're not the same. Okay, they're going to be different. Okay, there are a whole bunch of problems like this I can think of. And you can just do it with your friends, and maybe you have a teacher, local teacher that you can do it with. Well, I just wanted to ask you to actually subscribe to this channel if you haven't already. It kind of helping me grow this channel and helps other students, get reach this channel. If you like this kind of explanation or this kind of problems that I'm posting more or less every day, once a day, then please hit a like button. That also helps in the search engine. If somebody's looking for a problem similar to this and they can learn from it, maybe you can tell your friends about this channel. Well, take care and see you in another video. Bye.